Shall we start the session, sir?
Yes, we can start. Now I'm able to hear you.
Now I request Arudra to give a brief introduction about our resource person, Dr. J. Chelladurai, sir.
Thank you, sir. Good evening, everyone. It is an honor to introduce our esteemed speaker, Dr. J. Chelladurai. Dr. Chelladurai is an assistant professor in the Department of EEE at PSG College of Technology, Coimbatore, with 21 years of teaching experience. He holds an MTech in Power Systems from MIT Trichy and BE from GCT, Coimbatore. His research focuses on power quality, fans, and power electronics, and he has published 13 research papers in reputed journals. Beyond academics, he is deeply passionate about mentoring students and advancing innovations in power electronics. His expertise has inspired many young engineers to explore cutting-edge technologies in the field. Today, he will enlighten us on inverter controlling techniques, a key area in power electronics. Let's extend a warm welcome to Dr. J. Chelladurai.
Thank you. Thank you very much for your nice introduction. So the given topic to me is inverter control techniques. So in this session, I'm going to cover basic concept behind the inverter technology. Am I audible?
Yes, sir. You are audible, sir.
Yes.
And
yes.
the presentation also visible, sir.
Okay. Okay. Thank you.
Thank you,
So,
sir.
in this session, first topic I'm going to cover introduction to VSI and CSI. So here VSI means I hope everyone know voltage source inverter, and CSI means current source inverter. Next to introduction, basic principle of VSI. Then importance of VSI control parameters for different applications. And then control of real power, reactive power, and harmonics using the same VSI topology. In VSI topology, next to control the VSI topology, different PWM techniques we'll discuss. Then recent trends in inverter control techniques, and then introduction to closed loop control of inverter. So what is an inverter? In power electronic converters, basically there are 4 different types of power conversion we can do. One is AC to DC, DC to AC, DC to DC, and fourth very important topology is DC to AC conversion. So out of these 4 different power conversion topology, DC to AC converter topology will play a major role in industry as well as home appliances. And out of in these 4 different types of power converter topology, application point of view, the number of power converters used in any particular appliances is inverter topology. So inverter is nothing but it will convert DC into AC. So along with control the electrical input, we can control the along with conversion, it will control the output voltage magnitude. So here, very simple conversion, fixed DC voltage is converted into simple square wave AC. By using this simple conversion, or to implement this simple conversion, we can use different power electronic converter topologies. Using only 2 devices, or using 4 devices, or more than 4 for single phase topology. Similarly for 3 phase. In inverter topology, there are 2 different types. One is voltage source inverter. Second one is current source inverter. In voltage source inverter, the input voltage is considered as an ideal DC voltage source. Then by using power electronic converter, that is number of switches, we can convert this fixed DC into variable AC based on our different applications. In practical case, if suppose the input voltage is variable in nature within the given limit or design limit, we have to connect a capacitor across this DC source. So with the very large value of the capacitor, we can maintain the voltage magnitude across the input as a constant one. So this topology, frequently we have to call it as a VSI. In this VSI topology, the output current is purely based on the connected load. So here I can reverse, but output voltage can't be reversed. So it is a very simple DC to AC conversion power circuit with the IGBT along with the feedback diodes. This is DC to three-phase AC conversion topology. By using this voltage source inverter, we can convert this DC voltage into AC. Next to voltage source inverter, the second very important topology to convert DC into AC is current source inverter. In this current source inverter, practically there is no current source. So we have to get constant current source by using voltage source only. With voltage source, we have to connect a very huge size inductor to maintain the current magnitude in this input terminal as a constant one. Then by using again different power electronic switches, we can convert this DC into AC. So in this topology, the input current magnitude is maintained as a constant one. So the output voltage can be reversed, but the output current magnitude can't be reversed. So we can control the output current. So it is called simply it is represented as CSI. And the second diagram is, instead of indicating voltage source in series with inductor, simply it is with one ideal current source. Then types of current source converters. One is line commutated converter, another one is self-commutated converter. In line commutated converters, we have to use the turn on capability switches only. But turn off capability is not available in any switches. Example, SCR. So SCR is a latching device. We can easily turn on the SCR by using gate pulse. So once the device comes to on state, not possible to turn off by using gate terminal. Because of this reason, it is called semi-controlled switch. If we use this SCR to convert DC into AC in current source inverter topology, it is called line commutated converter. The reason is, so the line voltage, that is AC side, voltage zero crossing point will turn off the device. So example for this line commutated converter is the single phase or three phase fully controlled converter topology, or in HVDC system, anti-parallel connected to converter topology, we can exchange the power from one side into the other side, DC into AC or AC into DC. So to exchange the power from DC to AC, so already we know the fully controlled converter topology firing angle alpha is varied from 0 to 90 degree. It will act as a rectifier. Then if the firing angle alpha greater than 90, less than 180 degree, it will act as an inverter. So by using this line commutated converter to convert DC into AC, so we have to use SCR. The main drawback of using this particular line commutated converter is it will absorb huge amount of reactive power from the grid. So because of this reason, in most of the practical solar based renewable energy conversion system, this particular or wind based renewable energy conversion system, this particular line commutated converter topologies are mostly not preferable. Then second one is in current source converter topology, self-commutated converter. In self-commutated converter, instead of using SCR, it is fully control capability devices like transistor, IGBT, or MOSFET can be used to convert DC into AC. So by using this conversion topology, we can effectively convert DC into AC. So the same concept is represented here, thyristor-based line commutator converter, DC side with very high value of inductor. Then SCR is used in this line commutator converter. The turn-off time period is purely controlled by means of the AC side voltage. But in this converter, the main problem is it will collect the reactive power, or it absorbs the reactive power. So another one very important information related to this line commutator converter, the amount of harmonics injected into the power system network is also high. So we have to use filters. The same is with the specific load DC into AC conversion. If we use any specific load, then turn off these 4 thyristor is not an easy task. So we have to use some commutation techniques. So because of this reason, so in most of the practical applications, this particular line commutated converter or these DC into AC conversions, AC topology, especially using SCR is not preferable. The next one is self-commutated converters. In self-commutated converters, again, DC in series with the high value of the inductor, then power circuit using get turn-off capability devices. Then remaining things are same, but by using this only one small modification, we can exchange the power, both active as well as reactive. So for huge size power conversion, especially renewable energy conversion system, if suppose the wind energy conversion system capacity is in terms of megawatts, so we can prefer this type of self-commutated current source converter topology compared to voltage source topologies, PSI topology. But here we have to use this fully control capability devices. That is, by using gate terminal, we have to turn on and turn off the n number of switches available in the given power converter topology. So example for self-commutated converter using gate turn off thyristor. So one wind energy conversion system. The wind energy, variable wind energy is converted into AC into DC. Then again, here DC is converted into AC to inject the power into the grid. But using this particular topology, the main problem or limitation is so this gate turn off thyristor is having limited switching frequency. So because of this limited switching frequency capability, so the amount of harmonics injected into the power system network or the filter inductor and capacitor size is normally very high for these self-commutated converters with gate turn off thyristors. And the same converter topology, if we use for solar inverters, so the main problem in solar inverter based this current source inverter topology, it will inject very high earth leakage current. So to avoid this earth leakage current, we have to use transformers. So again, the transformer size is too big. So because of this reason, so this topology is not preferable for low power applications. Only this CSI topology we can use for very high power applications. So the recent trend in this current source inverter based wind energy conversion system. So instead of using the conventional gate turn off thyristor based concepts, so RB IGBTs can be used. RB IGBT means reverse blocking insulated gate bipolar transistor can be used to convert first stage AC to DC, again in second stage DC to AC. So by using this, the IGBT switching frequency compared to the previous devices is very high. So the overall efficiency and performance is better compared to the previous one. Then size and weight reduction is also possible. In general, the current source inverter advantages. Since the input DC current is controlled and limited, because of using this very high inductor, we can control and limit. If suppose any misfiring or switching short circuit is occurred means, it would not be a serious problem. Then peak current of the devices are limited. Then it can handle regenerative loads without freewheeling diode, because the voltage polarity can be reversed by using this current source inverter. So voltage polarity is reversed to forward current direction means, so we can easily get the power exchange. So the main disadvantage of using this current source inverters, see, it requires relatively a large inductor. That is the main problem. See, in this particular circuit, one DC to DC converter and then one DC to AC conversion, that is current source inverter topology with this very high value inductor. The purpose of using this DC to DC converter is, if suppose the voltage, input voltage, for example, from the solar energy conversion system, if it is a variable in nature, or to extract the maximum power from the given solar energy system, we have to use MPPT algorithms. So by using this particular simple buck DC to DC converter topology, we can maintain the voltage magnitude across these two terminals as a constant one. Then with the help of the remaining current source inverter topology, we can convert DC into AC. So here the main problem related to this current source inverter is, so the inductor size is too high. Then second very important drawback is the dynamic response is also very low. Then output filter requirements required suppress the voltage spikes is also very important. Then in common difference between VSI and CSI topology. In VSI topology, the input voltage magnitude is considered as a constant one, or we have to fix the constant DC voltage. In current source inverters, input current is constant. Then the output voltage does not depend on the load in VSI. But in current source inverter, the output current does not depend on the load. But the voltage in current source inverter purely based on load impedance. But in VSI topology, the output current is purely depends on the nature of load. And in VSI topology, in order to exchange the power, or if the load is having inductor, then feedback diodes we have to use to exchange the power from one side to other side. But in CSI topology, so without using feedback diode, we can exchange the power from one side to other side. Then basic principle of VSI, compared to, because of all these drawbacks of CSI topology, most of the practical applications, the preferable topology is VSI than that of CSI. See, the current magnitude or total power exchange is very high, normally in terms of megawatts, then only the CSI topology is preferable than that of VSI. So the basic principle of VSI is, so we have to consider here, or we have to fix the input voltage magnitude as a constant one. By using constant DC voltage source, so we can easily control the output AC voltage magnitude with the help of different control techniques. So by using this VSI topology, there are three parameters we can easily control. One is output voltage magnitude. The second one is output voltage frequency magnitude. The third one is output voltage phase angle magnitude. So based on the actual requirement, we can change the output voltage magnitude or output voltage frequency or output voltage phase angle. So with the help of different PWM techniques we can control. That's how we will see one by one. So again, in this slide, one AC to DC or DC to AC voltage source converter topology is indicated. So with IGBT and diode, we can easily exchange the power from AC to DC side or DC to AC side. So in this simple that is waveform representation, here voltage and current waveform. With respect to voltage, the current is lags by an angle. For example, let us consider phi. So now, if we analyze this waveform, voltage and current waveform, in first quadrant, it is indicated as 1. In first quadrant, see the voltage and the current magnitude. So during this period, both voltage and current are positive. So it will act as an inverter. Or simply, if you want to convert DC into AC, the inverter pole voltages, ABC voltage magnitude, if suppose more than that of grid voltage, then power will flow from DC to AC. That can be achieved in quadrant 2. Then in quadrant 2, it is indicated here, the voltage and current. So one is positive, another one negative. So the power is the reversed. That is, it will act as a rectifier. So it will convert AC into DC. Similarly, in quadrant 3, both are negative. So it will act as an inverter. Then in this duration, this fourth quadrant, one is positive, another one is negative. It will act as a rectifier. So simply by controlling the inverter output voltage magnitude and the phase angle, we can easily exchange the power from one side to the other side. Then further to understand this concept, so already we know, suppose two sources are connected through an inductor. So we can easily exchange the power from one source to other source simply by varying the voltage value. So in this vector diagram, forward power flow, it can be easily achieved by using this very simple representation. So for example, so with respect to VG, the VI voltage lags by an angle del, and the VI voltage magnitude is greater than that of VG, and the current IG is in phase with respect to VG. So to get the in phase current, we have to adjust this phase angle. And if the voltage magnitude is greater than that of VG, then power will flow from source 1 to 2. The same power flow, if you want to reverse, so just the voltage VI phase angle is leads with respect to VG. So by using an inverter, we can easily control the output voltage magnitude and output voltage magnitude and output frequency magnitude. And if it is required, we can control the output voltage phase angle. So in most of the grid connector inverter topology, the output voltage phase angle normally no need to change. So not output voltage phase and phase sequence. Phase sequence normally no need to change. Only voltage magnitude and phase angle we have to adjust. Frequency magnitude, it is aligned with the grid. So now by using this vector diagram, we can easily exchange the power from one side to the other side in opposite direction. The second one, instead of using this VI, that is phase angle, or the phase angle del value, suppose lesser compared to the previous case, but the voltage magnitude is less than that of VG, then we can operate the same converter in lagging power factor mode. In the previous case, the IG and VG, it is both current and voltage are in phase in nature. So if you maintain the both voltage and current as an in phase in nature, we can easily maintain the power factor value equal to unity. Similarly, in this case also, so during reverse power flow, VG and IG both are in phase in nature, but the current direction is just opposite. So we can maintain the power factor magnitude as a unity. So in this case, simply again, the voltage magnitude and the phase angle, only these two parameters are varied to change the lagging power factor mode from unity to lagging power factor mode. Or in leading power factor mode, we have to increase the voltage magnitude. Similarly, to operate the same voltage source inverter in lagging power factor mode and leading power factor mode in reverse power flow, we have to change the voltage magnitude and the phase angle. So simply in this bridge type boost PWM rectifier circuit diagram or grid connected VSI inverter topology, we can maintain the source side current and voltage always unity. And at the same time, we can exchange the power from AC to DC or DC to AC. So again, in this vector diagram, it is unity power factor operation. Second case, again, unity power factor operation, but opposite direction. So simply here, the inverter, especially VSI inverter, can be operated in 4 quadrants, simply by varying the voltage magnitude and phase angle. So further, by the help of the waveform, if the voltage and current waveforms both are in phase in nature, the active power flow from AC system to the converter DC side, it can be easily achieved. The same vector diagram what we discussed in the previous slides. Voltage and current both are in phase in nature. But here the inverter voltage phase angle is lags with respect to voltage, and the phase angle exactly if you are going to maintain to get the current in phase with respect to grid voltage, then unity power factor operation is possible. The second case, just opposite. So active power flow from the converter DC side to AC. So only the difference is again the current is in phase in nature, but 180 degree out of phase with respect to this. It can be easily achieved by changing the injected voltage leads with respect to voltage V, but the phase angle difference between V and VSC is del. So by maintaining this del value, we can get this current and V, IS and V in phase in nature. So second very important concept in any wind energy conversion system or solar energy conversion system, if suppose any particular wind or solar energy conversion system can be used to inject only reactive power if it is required. So for such applications, so how to inject only reactive power by using an inverter? So already we discussed, inverter can be used to inject real power or reactive power or combination of both. So to inject only reactive power with respect to voltage, that is the current is lags by an angle 90 degree. So how to get this 90 degree phase angle difference? Now with respect to V and VSC, both are in phase in nature. Then we can get this particular mode of operation. Similarly, in inverse also, the converter generating reactive power. So again, it can be achieved by shifting this current direction. So again, here it is easily achieved by varying the voltage magnitude of VSC. But we have to maintain the phase angle difference between V and VSC. So it can be easily understood by using DSI topology. We can inject real power or reactive power. So here the static synchronous compensator can be used to inject reactive power, and at the same time, that is we can charge if suppose capacity is available, means we have to charge the capacitor with the help of with the help of the power electronic switches or converter topology. That is, both real as well as reactive power flow can be easily controlled by using this BSI topology. So here in first quadrant, the P and Q both are supplying the power. In second quadrant, P and Q, then third and fourth quadrant, P absorbs and Q absorbs. In fourth quadrant, P supplies and Q absorbs. So another one very important control of this particular VSI topology. The same VSI topology can be used to inject only the required amount of harmonics. So in this particular diagram, so there are four different waveforms are indicated. One is VA sine wave. Then with respect to this, the load current assumed is a purely quasi-square wave. Then the current compensation required with the help of VSI is, so extract from this particular quasi-square wave, to convert the quasi-square wave into pure sine wave. So we have to extract the harmonic component present in this quasi-square waveform. So with the help of this harmonic current extraction, so if suppose that particular harmonic current extracted compensated current is used as a modulating signal to control any VSI topology, then we can easily convert the quasi-square wave into pure sine wave. So we can use the same VSI topology to compensate or to inject the harmonic current into the existing power system network. So simply, the voltage source converter can be used to inject only real power, or voltage source converter can be used to inject only reactive power, or combination of both real as well as reactive power, or sometimes the voltage source converter can be used to inject or compensate the harmonics in any point of common coupling. So the negative effects of harmonics, already we know. Simply for understanding purpose, here I have listed. So the harmonics is nothing but in any power system network waveform, if the waveform is non-sinusoidal in nature, then that particular non-sinusoidal nature of waveform contains fundamental component as well as number of other than fundamental frequency components. So because of this other than fundamental frequency component, the negative effects of harmonics are conductor overheating, then reduced life of capacitor, then false operation of circuit breaker due to zero crossing information, then increased iron and copper losses in transformers and generators, then communication interference and electromagnetic interference. So harmonics injected into the power system network or harmonics magnitude should be considered as one of the very important performance parameter for any voltage source converters. Then performance parameters of any voltage source converter or a general inverter, the number of performance parameters are available, like power conversion efficiency, amount of harmonics injected into the network, then grid synchronization capability, then anti-islanding protection, then DC link voltage regulation, then inverter output voltage and frequency control, the reactive power control, then over voltage and over current protection, grid compliance, response time and dynamic performance, lifetime and reliability. So all these different performance parameters are purely based on how to design the inverter configuration. Similarly, how to control the given inverter power circuit diagram. So it is purely based on the control and power circuit topology configuration. So here I am going to concentrate only to discuss about the how to control the total harmonic distortion, or what are the different methods are available to control the harmonics injected into the power system network with the help of different control techniques, especially PWM techniques, and then how to output voltage and frequency control is possible with the help of different uh, applications. Then grid synchronization. Grid synchronization is one of the very important parameter or control aspect of any inverter. With respect to grid, for example, in our conventional AC generators, if you want to synchronize with respect to grid by using dark lamp method, we can easily match the alternator output voltage with respect to grid voltage. Similarly, alternator output voltage frequency with respect to grid voltage frequency. Then alternator output voltage phase sequence with respect to grid. So all these three different controls we can easily achieve by using grid synchronization. That is dark lamp method we can use, and by using field control techniques we can achieve. The same kind of control we have to achieve. But in the real-time power system network, mostly the grid is controlled with the help of these huge size alternators. So it may be through hydroelectric power generation or thermal or nuclear. Then using renewable energy conversion, if you want to inject power into the power system network with the help of voltage source converters, so initially the voltage source converter we have to connect with the help of the grid voltage reference. So to get the grid voltage reference, different control methods or different measuring methods are available. So for example, zero crossing detector method, discrete Fourier transform, Kalman filter based concept, weighted least square estimation, etc. So each and every topology or control method has its own advantages and disadvantages in terms of how the system, real-time power system network voltage magnitude and voltage frequency and voltage phase angle is variable in nature in different conditions. Next, fundamental component of harmonics can be easily understand with the help of this coming slides to give very detailed information about the harmonics. So why sine wave inverter is preferable? Everyone know that it is compatibility with all appliances. Efficient performance of especially inductive loads, reduced electrical noise and interference, higher efficiency and lower power loss. Then compliance with grid and power standards. Then in harmonics, there are two very important performance parameters. Then is harmonic factor. It is nothing but RMS of nth harmonic divided by RMS of the fundamental. Then another one very important performance parameter, total harmonic distortion. So it is sum of all harmonic component except fundamental divided by fundamental harmonics. So frequently we have to use these two performance parameters to know about or that is tell about the quality of output, especially using voltage source converters. Then the importance of harmonics, that is harmonics or power quality means voltage quality is considered as one of the very important power quality. The reason is, so with the help of power electronic converter, if we try to drag the non-linear nature of the current from the grid, then this non-linear nature of the current will change the actual voltage wave shape because of the source to load impedance. The voltage drop occurred across the impedance will alter the load side voltage wave shape. So compared to current quality, voltage quality should be considered as one of the very important performance parameter, especially related to power quality. So the voltage quality will change because of the non-linear nature of the current taken from the grid. So how to control this? Then these harmonics can significantly impact both inverters and the larger grid system. So inverter, how it will affect means, so the actual inverter switching losses will change. We'll discuss in detailed way while discussing the PWM techniques. Then it will interference with equipment, reduced efficiency, decreased power factor, then component stress. So all are the very important drawbacks of these harmonics. In most regions, I have specified the grid codes. Example, in IEEE 1547, similarly IEC 610032 will clearly indicates the harmonic requirements. And in CEA, Central Electricity Authority, so in 2010 version, voltage harmonics level and current harmonics level, especially in grid connected system, is clearly indicated. The voltage harmonics should not exceed 5%. In current harmonics, especially individual current harmonics, if the n is greater than or equal to 2, n means the order of the harmonics, so should not exceed 3% with respect to the fundamental. Then total harmonic distortion value, it should be less than 5%. And international standards adopted in India, so IEC 610032, this particular international standard for harmonic emission is, so mostly that is adopted in India. The standard specifies the limit of current harmonics injected by equipment into the grid, including solar inverters, to prevent excessive harmonic distortion. So to understand further about the harmonics available in any waveform, so we have to use Fourier series method to analyze the given wave shape. So the Fourier series techniques, it will give the complete information. By applying Fourier series techniques, it will give complete information about the given wave shape. So complete information means it will extract the all other harmonics present in the given waveform. So simply mathematically, the f of t can be written as A naught and summation of the order 1 to infinity, then number of cosine and sine waveform. So where A naught is nothing but, so it will give the information about how much amount of DC component present in any given waveform. Then the remaining n number of frequency component present in this given nonlinear nature of the wave shape may contain number of sine and cosine waveforms. That is, all are pure sine and cosine waveforms. Then the actual mathematical expression for A naught, A n, B n. Then if you apply this particular formula to extract the harmonic content present in any waveform. So let us consider this very simple triangular wave shape. In this simple triangular wave shape, this particular waveform is a purely non-sinusoidal nature of the waveform. So in this non-sinusoidal nature of the waveform, if we apply the Fourier series expression, this Fourier series expression, here I have indicated the fundamental, that is omega t, then 3 omega t, third order harmonic content, then fifth order harmonic content, seventh order harmonic content, and ninth order harmonic content. Only five different harmonic orders or harmonic waveforms, and that particular mathematical expression is given. So after applying the Fourier series for this particular wave shape, we will get this mathematical expression. So now first wave, that is fundamental wave, magnitude is 80 by pi into sine omega t. So graphically we can represent this fundamental component. Then next, with this fundamental component, the second third order harmonic component, magnitude is 80 by pi into minus 1 by 9, then sine 3 omega t. 3 omega t is nothing but third order harmonic component. If we add these two sine waves. So now by adding these two sine waves, the actual wave shape is changed very near to triangular wave shape. Further, if we add the fundamental plus third order plus fifth order, it is more near to the triangular wave shape. So similarly, then seventh order and then ninth order. So up to ninth order, almost it is equal to triangular wave shape. So similarly, if we add the up to nth order harmonic component, we will get the given input triangular wave shape. The purpose of analyzing this particular wave shape is so to understand about what is mean by harmonics and what are the components are available. Here in this particular this triangular wave shape, the triangular wave shape positive half cycle and negative half cycle both are same. Because of this reason, the even order harmonics are totally absent. So in power electronic converters, while converting or controlling the positive set of devices and negative set of devices, symmetrical firing pattern or symmetrical nature of positive set of voltages and negative set of voltages, if we get means totally we can eliminate the odd even order harmonics totally. We can eliminate the even order harmonics. So if suppose such kinds of control is not used in any power converter topology, then even order harmonics will also present. Then it is very difficult to eliminate all such harmonics, or we have to use very huge size inductor and capacitor to eliminate all such harmonic component. So to understand this concept, so second waveform is simple square wave, because by using an inverter, quasi square wave or square wave, mostly we are going to get. So in square wave, again, in this simple square wave, if you apply the Fourier series, we will get this type of equation. Again, so this positive and negative half cycle both are same. So fundamental component of this square wave contains 400 by pi into sine omega t. Then add the fundamental with the third order harmonic component. In this particular square wave, the third order harmonic phase angle is entirely different compared to the previous triangular wave shape. Now by adding these two, the wave shape is entirely different. That is third order harmonic component along with fundamental. So this particular wave shape is very important one, because one of the PWM technique, third order harmonic elimination technique, we have to do the same fundamental plus third order harmonic component. Wave shape is used to produce the PWM pulses. So to eliminate that is particular order of the harmonics in any inverter output. So further, fifth order harmonic component, then seventh order harmonic component, then ninth order harmonic component, it is almost near to square wave. So similarly, the next 11 and 13, etc., we are going to add. So then we will get pure square wave case. Then Fourier series expression if we apply for pure sine wave. So if you apply the Fourier series expression for the above 3 A0, then B1 and other even order harmonics and odd order harmonic component present in pure sine wave. So the DC component present in pure sine wave always equal to 0. Then AN coefficients is equal to 0. Similarly, BN coefficient is equal to 0. So only we will get fundamental component alone. So because of this reason, always we have to use pure sine wave for any electrical appliances. Then inverter applications. So inverter can be used for standalone applications or grid connected configurations. In standalone applications, for example, in motor drives, AC is converted into DC, then using a DC link inductor and capacitor, so we can get the smooth DC. Then again, DC is converted into variable AC and variable AC frequency. Here, the phase angle magnitude, mostly no need to change. So here the VSI topology can be used to control only the output voltage and frequency. Output voltage and frequency. So with respect to the especially motor drive, so the other important performance parameter related to the inverter is harmonic control. So harmonic control can be easily achieved, or harmonic reduction can be easily achieved by using or by changing the switching frequency. Related to switching frequency, different inverter configurations are available based on the applications. Simply here one of the very important information is, if the load capacity is very high, or load power requirement is very high, or it may be VSI connected with respect to grid, the amount of power injected into the grid is more, especially using VSI topology, then the switching frequency should be limited. The reason is, so while increasing switching frequency, already we know in each and every turn on and turn off process involves the switching power loss across each and every switch. So before going to increase the switching frequency, the load parameter, especially load power magnitude, should be considered as one of the very important performance parameter. Then second application in induction heating. In induction heating, AC is converted into DC by using conventional rectifier. Then DC is converted into high frequency AC by using a VSI topology. Again, based on the different application requirement, here I have indicated different operating frequency. So in this particular case, the output voltage magnitude most of the case constant, but output voltage frequency magnitude we have to adjust by using VSI topology. Then similarly in UPS system, in uninterrupted power supply system, AC is converted into DC. Then we can store across battery source. Then again DC is converted into AC by using voltage source inverter topology. So again in this particular case, so suppose the connected load is standalone application means, for standalone application, output voltage magnitude we have to maintain it as a constant one. Then frequency magnitude we have to maintain it as a constant one, irrespective of the connected load. So here again by using voltage source inverter, we can maintain output voltage magnitude as well as frequency. So with respect to the power demand, here again switching frequency limitations are given. Then another one that is interesting application in welding power supply. In welding power supply, the basic requirement is very low DC voltage magnitude, with very high current requirement. So to get the very low voltage and high current loads, conventional welding power supply using transformer. If we use very high current transformer in AC side, especially in 50 Hz or 60 Hz AC side, the size of the transformer is too bulky. So with the help of VSI topology, so we can reduce the welding power supply size drastically by using this power converter topology arrangement. Here AC is converted into DC with the help of diode, bridge rectifier, and then this DC is converted into very high frequency AC. So the purpose of increasing the frequency magnitude in this welding power supply is to reduce this step-down transformer size. So now we can get very low voltage by using this very high frequency step-down transformer. Then again we can convert AC into DC. So finally here we will get low voltage, high current DC output. So again here with respect to the load demand, different switching frequency requirement is given for the in this voltage source. The next, in solar and wind energy conversion system, different topologies are available. In wind energy conversion system, here I have indicated both It is AC into DC conversion, DC into AC conversion with the help of voltage source converter, IGBT based voltage source converter. So the purpose of using first stage AC to DC with the help of IGBT based AC to DC conversion is we can maintain the source side current wave shape, or we can improve the quality of the current taken from the wind energy conversion system. Similarly, the second one, DC to AC, with the help of VSI topology. So we can easily inject real power alone or reactive power alone, or both real as well as reactive power magnitude by modulating the switches. So similarly, next one is in solar energy conversion system. So DC to DC conversion, here boost converter topology is indicated. We can maintain the DC voltage magnitude as a constant one. Then DC is converted into AC. Then in solar and wind energy power conversion system, again, different configurations and topologies are available. So again, one of the very important performance parameter to select the switching frequency of the particular VSI topology is based on the power magnitude. In string inverters, 1 kilowatt to 100 kilowatt, the preferable operating frequency is 2 kilohertz to 20 kilohertz. Then similarly, central inverter based topology, 100 kilowatt to 5 megawatt, 1 kilohertz to only 5 kilohertz. That is the output switching frequency is limited up to 5 kilohertz. For micro inverters, the switching frequency is increased up to 100 kilohertz. Similarly for wind energy conversion system. Then another one very important that is configurations, which is used nowadays for maintaining the grid stability with the help of renewable energy conversion system, that is battery energy storage system. So with the help of battery, so any sudden power demand can be easily achieved with the help of this power converter topology. Here DC is converted into again DC, then DC to AC. So again here with the help with respect to the power demand, different switching frequency ranges are represented. Then EV application, and again in EV application, the voltage source inverter will play a major role. Each and every that is topology, finally we can control by using voltage source converters. There are three parameters can be easily controlled. One is voltage magnitude, second one is voltage frequency magnitude, third one, if it is required, voltage phase angle magnitude. So only by controlling these three parameters, all the required industrial control needs we can achieve. Then another one, the boost PWM rectifier, it is very popular for any low power to high power applications. So we can get pure sine wave, especially current wave shape can be easily improved with the help of this voltage source inverter configuration. Then to control the VSI topology, PWM, that is pulse width modulation. So in PWM or pulse width modulation technique is used to control all these three parameters: voltage magnitude, voltage frequency magnitude, and phase angle magnitude. In pulse width modulation means each switch on time period is controlled with the help of PWM principle. In general, pulse width modulation can be achieved with the help of two different wave shape. One is carrier wave, another one is reference wave. In this representation, to understand the principle of PWM, short tooth waveform is considered as a carrier. Then pure DC voltage is considered as a reference voltage. So now, by comparing these two wave shape, that is DC voltage and triangular carrier, we can easily adjust the pulse width. This pulse width can be directly connected through driver circuits to turn on and turn off. That is a number of switches available in the given power dynamic converters. So the main advantage of using pulse width modulation technique is simply voltage control is easy. Then harmonic we can control easily. Then especially while increasing the switching frequency of PWM technique, higher order harmonics can be increased, or lower order harmonic component magnitude we can decrease. So by reducing the lower order harmonics, again the filter requirement, inductor capacitor, we can reduce. So main disadvantage of using PWM techniques, so the switching losses will increase. So related to these switching losses, already we discussed for different applications, that is how to fix the switching frequency. For very high power applications, we have to limit the switching frequency operation. Then reduction of available voltage, then EMI problem. So very high switching frequency conditions can be easily adjusted or compensated with the help of simple, very low size inductor and capacitor. That filter circuits design is very simple. Classification of PWM technique, research point of view, different methods are available. Each and every PWM technique has its own advantages and disadvantages. Here we'll discuss about this unipolar and bipolar. Two types of PWM techniques are available. Then in unipolar and bipolar, we can use these different types of PWM techniques. So one is single pulse width modulation, multiple pulse width modulation, sinusoidal pulse width modulation, then modified sine PWM, third order harmonic PWM, 60-degree PWM, trapezoidal, staircases, stepped PWM, delta modulation, and one of the very important PWM techniques, space vector pulse width modulation technique. So in single pulse width modulation technique, only one pulse per half cycle. So only one pulse per half cycle can be generated with the help of these two. One is carrier, another one is reference. Here reference waveform is simple square wave. So by comparing these two, so this particular positive half cycle waveform, similarly negative half cycle waveform, we can get by controlling the positive set of devices and negative set of devices. Then advantage of using this. So already we discussed one of the very important performance parameter for any voltage source converter is harmonics. By using this simple quasi square wave output, this quasi square wave output normally contains very high lower order harmonic component. Here modulation index is one of the very important performance parameters, especially in PWM techniques. Modulation index is nothing but the ratio of V reference voltage or modulating signal with respect to carrier, or V reference divided by V carrier is a modulation index. By varying the modulation index, how the each and every harmonic component will change. In this particular graphical representation clearly indicates that with the help of a single pulse PWM, the third order harmonic component is very high, especially under lower modulation index. And moreover, the distortion factor is also so increasing with that is very low modulation index. And higher order harmonic component is also present. So here minimum harmonic order will start from 3. Then to reduce the lower order harmonic component, next method of pulse generation is multiple pulse width modulation technique. By using this multiple pulse width modulation technique, the number of pulses per half cycle is increased. So if we compare the actual total on time period, here for example, let us consider the 50 Hz AC output. The total on time period is out of 10 milliseconds. Assume 5 millisecond period is turned on. So to get the same 5 millisecond on time period, let us consider 1 millisecond on, 1 millisecond on, 1 millisecond, like that 5 pulses per half cycle. So total on time period, if we are going to consider in this waveform, again 5 millisecond only. But compared to the previous case, with the help of multiple pulse width modulation technique, which is supposed used in inverter topology, so a lot of advantages you can get. That is, the amplitude of lower order harmonics are eliminated. Then higher order harmonic component magnitudes may increase, but it can be easily compensated or that is cancelled or mitigated with the help of very low size filters. Next, very popular modulation technique, that is sinusoidal pulse width modulation. In sinusoidal pulse width modulation technique, again we have to use two waveforms. One is triangular wave, another one is sine wave. So with the help of sine wave with the triangular comparison, so one of the very important observation is over the period of each, that is half cycle, the pulse width duration is purely followed this sine wave shape. That is, the pulse width duration is different. So because of this particular different pulse width wave shape, the output voltage wave shape is during positive half cycle, number of pulses we can decide by changing the carrier frequency. Then compared to the previous two cases, the output voltage quality can be drastically improved. So only in terms of reducing the lower order harmonic component, and at the same time higher order harmonic component will increase. That is not a major issue. That can be easily eliminated with the help of lower size filters. Then here, for example, number of pulse per half cycle is 5 means. So the minimum lower order harmonics will start from 9. So these are all the very important advantage of using sinusoidal pulse width modulation technique. Then next to sinusoidal pulse width modulation technique, modified SPWM. The purpose of varying purpose of using different PWM techniques only to improve the output voltage quality. So output voltage quality is more means the actual current injected from converter to grid will also improve, or the current actually flow from converter to any specific load may change. So by the help of this small variations, we can improve the overall system performance. Already we have listed efficiency, then voltage quality, current quality, then any specific current, that is order of the harmonic component, magnitude reduction, etc., can be easily achieved with the help of different PWM techniques. So next to sinusoidal pulse width modulation technique, the space vector pulse width modulation technique is another one very important PWM techniques. Modified. In this modified SPWM technique, it is from 0 to 60 degree. So there is a carrier wave. Then 60 to 120 degree, there is no carrier wave comparison. Then again 120 to 180, there is a carrier wave. Simply by introducing this kind of small modification to produce the different pulse width during positive half cycle and negative half cycle, it's a lot of advantages. So by using this method, the fundamental component is increased. Fundamental component means, so by using DC to AC conversion, the effective fundamental output voltage magnitude or the DC bus utilization is also one of the very important performance parameter. The DC bus utilization compared to the previous 3 different pulse width modulation technique with respect to this modified SPWM is more. So, and another one important advantage compared to the previous case, the number of turn on and off period is very less. That is, switching frequency is very less. So we can drastically reduce the switching power loss, and hence we can increase the converter efficiency. The next, third order harmonic injected SPWM. So only the required difference is, so instead of comparing the modified SPWM or conventional sine wave is used to compare with the high frequency carrier. So with respect to this triangular high frequency carrier, the modified sine wave, that is fundamental plus third order harmonic component, if we are going to add, see here, the fundamental and third order harmonic component, if we are going to add, so you will get this type of waveform. That is, with fundamental and third order harmonic component waveform is used to compare with high frequency carrier. It will drastically change the performance of an inverter. So one of the very important advantage of using this technique is the DC bus utilization is 15.5% more than that of SPWM technique. Next, very important, that is types of PWM techniques. All these previous concepts can be used in unipolar or bipolar arrangement. Unipolar means, let us consider this single phase inverter topology. In this single phase inverter topology, 4 switches, the switch S1, S2, S3, S4. So in bipolar switching configuration, one sine wave is compared with the high frequency carrier. That is, one sine wave is compared with the high frequency carrier. Then output pulse is directly connected to switch S1 and S2. And the inverted form of this output pulse is connected to S3 and S4. So during positive half cycle and negative half cycle, the state change occurred by using bipolar switching technique across the output is, the output voltage is varied from minus VDC to plus VDC. And output voltage overall, that is wave frequency or switching frequency, is similar to that of the carrier frequency. For example, carrier frequency is 1 kilohertz, means the output voltage, that is switching frequency is, or normalized frequency of the output voltage is 1 kilohertz. But in unipolar technique, we have to change the modulation. That is, the same sine wave is compared with respect to carrier, but we have to use 2 different sine wave. So one is positive, another one sine wave is 180 degree out of phase with respect to the first one. So now, by comparing the first case, positive sine wave with respect to the same carrier, the output voltage, 2 different output voltage is required. Here we can easily understand the unipolar PWM pulse generation. VR is nothing but reference voltage. PC is a carrier voltage, that is short tooth wave. But we have to use 2 comparator in unipolar PWM. One is positive VR, another one is minus VR. Minus VR means with respect to positive VR, 180 degree out of phase waveform is used to compare with the same triangular wave shape. Then we will get 2 different pulse output. From this first pulse output, use one NOT gate. Then we will get second one. Similarly, from this second one, 4th output pulse we can get. So now by using S1, S4, S3, S2. So from this S1, S4, that is first arm upper switch and first arm bottom switch. Similarly, second arm upper switch and second arm bottom switch, if we try to connect, then compared to bipolar PWM, so here understanding purpose, the SPWM technique with the unipolar output voltage, then the actual load current, then IDC means the DC current waveform. These 3 different waveform we can analyze in order to compare the unipolar and bipolar topology. So the system parameters are VDC 100 volt, then resistor, inductor and switching frequency 1 kilohertz, then modulation index is maintained at 0.8. Then fundamental frequency component, that is output voltage, fundamental component is considered as a 50 hertz. So now if we compare the SPWM pulse generation with unipolar configuration, the current ripple. And another one very important observation is the voltage wave shape. The voltage wave or voltage magnitude is changing from 0 to positive during positive half cycle, then 0 to negative during negative half cycle. So here one of the very important observation using unipolar PWM technique is the switching frequency is only 1 kilohertz, but the actual effective switching frequency of the output is 2 times of fundamental component. Because of this higher switching frequency operation in unipolar PWM technique, the current ripple magnitude is very less, very less. And similarly, but the one of the very important drawback available in this unipolar is DC side current ripple is more. If DC side current ripple is more means the DC side capacitor size slightly may change. Next one is another one very important observation, the THD value present in output voltage wave shape. So in this output voltage wave shape, by using 1 kilohertz switching frequency, the switching frequency and the THD value is very important one. The output voltage here, the average switching frequency is 2 kilohertz. 2 kilohertz. Because of this reason, the most of the harmonics are shifted towards the 2 kilohertz. 2 kilohertz. If the harmonic magnitude or that is harmonic content is shifted towards the higher order harmonic content, means that can be easily eliminated with the help of that is small size filters. So next to the same load and source is used to convert a DC into AC with the help of a bipolar output. Using bipolar output, the current ripple is low. So another one very important observation, with the help of bipolar output, the DC voltage, output voltage variation is from minus to plus. So during positive half cycle and negative half cycle, minus to plus. So here the output voltage is AC, that is pulsed AC. If we eliminate the unwanted frequency component in this output voltage, we can get pure AC. But the output average switching frequency is only 1 kilohertz. But in unipolar, it is 2 kilohertz. So another one advantage is here IDC current ripple is less. So small size capacity is enough to maintain the DC link voltage magnitude as a constant. But at the same time, that is here the voltage stress applied across the switch using bipolar PWM technique is 2 times of your VDC. So the switch voltage rating is 2 times more than that of the unipolar PWM technique. And another one very important drawback of using this method, here the output voltage harmonics will start near from 1000 hertz. So the lower order harmonic component is more compared to the previous case. So these are all the very important comparison between bipolar and unipolar. So based on the actual applications, we have to select in most of the practical applications, instead of using bipolar, unipolar PWM technique is mostly preferable one. So I hope already we know that is the how to avoid the shoot through fault, especially in voltage source converter. In voltage source converter, to avoid the direct short circuit, always we have to allow the dead band between the upper switch and lower switch. So normally for IGBT based inverter topology, 2 to 4 microsecond delay is more than enough to avoid this shoot through fault. Then by using this simple logic, we can totally avoid the shoot through fault. The next very popular PWM technique is space vector pulse width modulation technique. In space vector pulse width modulation technique, it is not like conventional sinusoidal pulse width modulation technique. So with the help of this space vector pulse width modulation technique, the switches on period and off period simply decided with the help of this vector. So for example, so this Vs is the actual required output, or this Vs is used as a control parameter to produce a 3-phase AC output. So this particular Vs is nothing but vector sum of Vrn, then Vbn, then Vyn. Vector sum of these 3 will give this particular value. In order to get these 3 voltage vectors, so in 360 degree period, we have to use this space vector pulse width modulation technique. So we can easily understand this space vector pulse width modulation technique by using these 3 plus 3, 6 plus 2 different vectors. Or that is with the help of these 6 plus 2, 8 different sectors, we can easily analyze the actual output voltage. So for example, here in first leg, upper switch is turned on. 0 means bottom switch on condition. 1 means upper switch on condition. So 0, 0, 1 means first leg bottom switch off, second leg bottom switch off, third leg upper switch on. So now we can connect the, for example, let us consider star connected R load across R, Y, B phase. So now if you are going to consider the VDC supply. When these three switches are in on condition means we can easily analyze VAN voltage, that is star connected output, phase voltage and line voltage. Similarly, the second sector, third, fourth, fifth, sixth, and then two null vectors. Null vectors means, say it may be in 0, 0, 0 condition or 1, 1, 1 condition. 0, 0, 0 condition means all the bottom switches are in off condition. 1, 1, 1 means all upper switches are in on condition. Under this particular mode of operation, output voltage will be equal to 0, 0. So in conventional space vector pulse width modulation technique, we have to use these two null vectors. So to produce this, so the actual VAB and VAN voltage is written in matrix form. So finally, based on the different voltage vectors, that is 8 different voltage vectors we can consider. There are 8 different switching states we can consider. Out of 8, first state 0, 0, 0, output voltage always 0. Similarly, last case 1, 1, 1, output voltage is equal to 0. So the remaining 6 different states will produce the different output voltages. So to analyze this, consider the star connected R load, then try to derive the VAN, VB and VCN. You will get this 2 by 3 times of VDC during this particular mode of operation. Similarly, minus 1 by 3 for VBN and VCN, etc. So simply compared to the SPWM technique, the space vector pulse width modulation technique offers very good DC bus utilization. Then second one is the harmonic content present in space vector pulse width modulation, especially lower order harmonic content is less. Then complexity point of view, complexity means in order to, with the help of microcontroller or microprocessor or DSP, if you want to produce the pulses, gate pulses using SPWM technique or SVPWM technique, compared to SPWM technique, SVPWM technique that is requires somewhat complex algorithms. Then switching frequency in space vector pulse width modulation technique, the switching frequency is less compared to sinusoidal pulse width modulation technique. So efficiency is obviously more in space vector pulse width modulation technique. Then another interesting PWM technique, number of PWM techniques are available. Another one very important PWM techniques. Now I want to explain about bus clamping PWM technique. It is similar to that of space vector pulse width modulation technique. In bus clamping PWM technique, here I have listed 3 different bus clamping PWM technique. First, bus clamping PWM technique means one of the phase gets clamped to either positive or negative DC bus, resulting in reduced number of switching and switching losses. That is the main objective. So instead of using continuous turn on and turn off with the help of space vectors, using bus clamp PWM techniques. So out of 3, one particular phase is clamped, either 111 state or 000 state. Then the switching losses performance and amount of harmonics injected in the produced by means of this VSI topology is improved. So now three different bus clamping PWM techniques here I want to explain. One is 30-degree bus clamping PWM. In 30-degree bus clamping PWM, just in each carrier waveform duration, the R phase, Y phase, and B phase. In this particular 30-degree bus clamping PWM technique, see here the B phase is off. The remaining two switches are turned on and off. Similarly, for the next 30 to 60 degree, so what is the actual switching pattern? The switching pattern will not change during this period or in a particular sector. But one of the very important that is assumption or consideration using bus clamping PWM technique is, in this bus clamping PWM technique, one of the phase is clamped. Here B phase is clamped, here R phase is clamped. But in SV PWM technique, there is no clamping arrangement. All the three phases are turned on and off with different pattern. These turn on and off patterns are purely based on the sector, or that is where the actual voltage vector is required. For the particular or corresponding voltage vectors, we have to turn on and off the switches. So due to lack of time, simply I want to just compare these three techniques. So with the help of this simple load, RL load, I have compared the SVPWM technique, that is conventional SVPWM techniques. I think here 30-degree PWM and then 60-degree. Another one is advanced bus clamping PWM techniques. So with the help of this advanced bus clamping PWM technique, the current THT performance is, compared to all the three different space vector pulse width modulation technique, it is better. Then very simple, this is a very interesting that is control technique for inverter. Simply I will complete within 5 minutes. So this one is optimal switching frequency scheme, which is used in grid connected converters. The optimum switching frequency converter configuration means, shall I continue? Are any questions?
Sir, you can continue, sir.
Okay. Just within 5.
At the end of the session, we shall ask participants to ask the questions.
Okay. Just one or two very important information related to this. So in optimal switching frequency scheme, see here, with respect to this fundamental voltage, the switching frequency magnitude. Normally in any PWM technique, the switching frequency magnitude always constant. But some other different PWM techniques are available to improve the performance of VSI. So one of the method is variable switching frequency concept. In variable switching frequency concept, again, based on the load condition, we can change the switching frequency magnitude. For example, simply understanding purpose, if the connected motor load is only 50%, for 50% load condition, the switching frequency magnitude we can increase. Then we can get better performance, better efficiency, better harmonic that is performance. The same motor, if suppose running at 100% load or rated load. So under rated load condition, instead of using higher switching frequency operation, lower switching frequency we have to use. So based on the load demand, we can change this lower switching frequency or higher switching frequency mode. So another one very interesting information. So during this sine wave, that is fundamental waveform. So during this zero period, maintain very high switching frequency. For example, here 400 kilohertz is used. Then gradually reduce the switching frequency. When the peak of sine wave, the switching frequency magnitude is less, then further increase the switching frequency. Near to zero, it is very high. The purpose of using this very high switching frequency near to zero with respect to the fundamental output voltages, so we can reduce with respect to this particular current or voltage waveform. Suppose output current is sinusoidal. During this period, the current magnitude is very less. So we can increase the switching frequency. So by using this, the efficiency magnitude is drastically we can change. Similarly, the instantaneous switching losses also we can modify. So interested can try to that is implement this particular concept, variable switching frequency with respect to the output voltage wave shape over the period of 1 full cycle. Then another one very interesting information, the recent trend in grid connected inverter topology is grid forming inverters. So grid forming inverter means simply understanding purpose the conventional grid connected system available in India or that is most of the European countries. So the amount of renewable energy power injected into the power system network is always limited one. The reason is most of the grid connected inverters will work based on the grid following inverters. The grid following inverter means the grid voltage and grid frequency is actually used to control the inverters. Inverter means that is the periodic pulses are generated with the help of grid reference with the PLL. So instead of using this, or if you are going to use this method, the amount of power injected into the existing power system network is approximately less than 50%. The reason is N1 should that is operate or maintain the voltage and frequency of the grid. So the recent trend is with the help of high-end control algorithm with the help of battery charging system or battery storage with high-end control algorithm of inverters. So we can increase the penetration of renewable energy power into the grid up to 100%. So I saw in some literature in US, one or two there is places completely total power is supplied with the help of this grid forming inverters. So grid forming inverters will synthesize the that is conventional power generating system. And comparison between these two, so these grid connected inverter topologies, I hope already you know. In control point of view, these two parameters are very important. One is alpha, beta, and D2 transformation, mostly used to control the grid connected or any standalone inverters in closed loop. So popular techniques, current control technique. Another one is PQ. In current control techniques, only 2 PI controllers enough. But in voltage control, it's a PQ control techniques. We have to use 4 PA. So there is a major difference. So, thank you. Thanks for your patient listening. If you are having any questions, you can ask.
Now the session is open to participants. Participants can ask questions. Sir, a question in chat box, sir. What is synthetic inertia?
So synthetic inertia related to in any there is grid connector configuration. Line following inverters normally use the stiff grid. First, the difference between stiff grid and weak grid means in stiff grid the voltage and frequency magnitudes are maintained as a constant one with the help of huge size alternators, or huge size power supplies. It may be hydro or thermal or nuclear. In weak grid system, the voltage and frequency magnitude may change. So with the help of battery storage along with the inverter high-end control algorithm based inverter configurations, so we can easily maintain. Even though there is no stiff grid configuration, we can easily inject or penetrate the more amount of renewable energy power into the grid system. But conventional inverters, conventional power system network, that is the immediate power demand, can be easily adjusted with the help of the inertia. The same kind of operation we can get with the help of inverters.
Any other question from the participant side? If there is no question, sir, shall we close the session, sir?
Yes.
Thank you, sir, for the very detailed session on controlling techniques of inverter.
Actually, I thought to explain the SPPWM technique in detailed way, but due to lack of time, I quickly covered.
Yes, sir. Only 1.5 hours allotted.
Yes,
sir.
yes.
Okay, sir.
Thank
Now
you,
I
thank
invite. Thank
Yes.
you, sir. Now I invite Anuleka Pandi to give vote of thanks.
Thank you, sir. Good evening, everyone. On behalf of the organizing committee of ATAL 6-day faculty development program, I extend our sincere gratitude to Dr. J. Chelladurai, Assistant Professor, PSG College of Technology, for his insightful session on inverter controlling techniques. His expertise in power quality, facts, and power electronics has given us a strong technical foundation in inverter-based resources and control strategies. We truly appreciate his time and valuable insights. Thank you, sir, for sharing your knowledge with us.
Thank you. Thank you very much.
Sir, thank you, sir. Thank you for your time, sir.
Okay, thank you.